Okay, it's time to start. My name is Pavel Skribtsov. I will be talking today about deep learning. The challenging name says that it's a handcrafted code killer, and we will reveal why is that. So I guess some of you present on my yesterday lecture. So one of the questions that we left yesterday untouched was feature extraction for pattern recognition. If the mechanisms for recognizing objects are more or less now formalized, then the question was, how do we now select features for a particular pattern recognition problem? And it was always a difficult decision, because for every pattern recognition problem, people have to think on what kind of features could be discriminative, could help recognizer to differ between different classes. Let's look at this, I call it roadmap. So from object that we are going to classify to the final class membership, there are a few steps. So first of all, we get some data from the object. Well, I call it data because it can be unstructured information like arrays of pixels or maybe even multiple images. This can be wave audio file of the speech that we need to classify. This can be different arrays of sensors measurements of the object. So these are yet not features. I would call them data. And from this data, we need to run certain feature extraction algorithm that transforms this data into a fixed number of fixed vector of a certain number of parameters of characteristics that we think describe somehow this object enough to distinguish it from one and assign it to a certain class. So after feature extraction, we need to receive n-dimensional feature vector that is later submitted to the pattern recognition mechanism, which in turn give us class membership. So as I say, pattern recognition covers this part. So as you have feature vector, then there are several pattern recognition methods, and we covered a few of them, that allows you to make training sequence, feed it into the training algorithm, train classifier, receive its state, and then use some existing classification algorithm with the state to classify objects. And as I said, the question remains, how do we do this part? Now, another thing that's worth noting is that to train classifier, you need to prepare a training sequence. And training sequence, as we discussed yesterday, contains of examples of feature vectors of the objects with the corresponding class labels. That is, it's basically a table with columns where each column is a certain feature and the last column is the class label. Like, for example, these features belong to an object from class 1. The next line, these features belong to an object class 2, and so on. And this is usually done by manual work. So, for example, if you classify images, you need to have certain software that allows you to surround the object that you need to be able to recognize with a rectangle and assign manual label. So as the number of training examples must be quite high for pattern recognition, this can be sometimes a costly and lengthy process for labeling these data sets to train the classifier. So one of the targets that we want from deep learning is that how do we do not do much of this labeling part? Because we humans, we don't have that much labels coming to our mind when we learn something. Usually we're just looking at various objects and we start to recognize one object from another even if we don't know which class it belongs to. It's just later somebody tells us that this is chair and this is lamp. So basically just a small number of labeling information comes to our mind, and we do most of the job by ourselves. So it's interesting, how do we make this and try to repeat this in artificial system. To build this artificial system that extracts feature, we first of all need to ask ourselves the question, why do we need features at all? Why just can't we feed the whole data from the object to the classifier, like just submit all pixels, submit all wave samples in a wave file, and so on. Well, the problem here is that in this case, we have a highly multidimensional feature space. So we can represent each record as a point in a multidimensional space where each coordinate represents some kind of characteristics of the object. And the problem here is called the curse of dimensionality, that tells us that in spite of that we want to make a better life for our classifier and give it more information. Intuitively, we may think that giving more information about object helps to classify object with more precision. But the curse of dimensionality tells us that this is not always true. And I can show you a couple of examples that you will be able to feel what the problem is. For example, here is the toy data set. And these are two features of some objects from two classes, 0 and 1. So for those of you who sit in the back, I can quickly read it. So 3, 7, class 1, 2, 8, class 1, 0, 4, class 0, 10, 4, class 0, and so on. So can you guess what's the dependency between the features and the class in this simple example? How would you classify the object with the features 9 and 1? One person knows about, two, please? Yeah, so if we add and get 10, then it's class 1, so it was quite easy. Now, suppose we have this problem, and we have this data from which we need to, again, retrieve the class label. So you have now more data. You should be able to do it with more precision. I helped you, so it should be more easier than in this case. Can you do that? That's what is the problem of the curse of dimensionality, because you now may have multiple guesses. Whether it's this column is influencing the data, or that column, or maybe this is just a noise and distractor. And it's extremely now difficult to understand what is the decision rule here. Or even if we, for example, decide certain decision rule, it just may be wrong. We accidentally picked noise in some column for the actual source of data, and in fact, it will not help us to classify new objects where this not hold, where these rules not hold. So in this particular case, the answer was easy. It was for the numbers which are higher than 2, it's class 1. And for the other ones is class 0. So this is first example where you feel that too much data is bad. Or you need to have too many examples to really throw out things which do not really help you to solve the problem and extract the decision and focus on the columns which really make sense for your problem. Now, you all play in your childhood the game Battleship or Sea Battle. And let's consider this game. For example, we can consider this game in different number of dimensions. Suppose we play Battleship in one dimension, just 1D Battleship game. So how do you think how many fires you need to make approximately to understand the positions of the enemy? You just tell guess a random guess a number. There is no correct answer, but you may say 6, 5, yeah. So just not a big number of fires, and then you can understand which areas of this space are belong to class ship and which do not belong to this class, yes? Which belong to the class C. Now let's consider two-dimensional case. In this case, as you remember, the average number of fires you need to make to study this space, how everything is organized in the enemy, is something like, can anybody tell? Just a number. If it's 10 by 10, then the maximum number of fires possible is 10 multiplied by 10, right? It's 100, but usually it never goes to 100. So it's like 50 or 60 moves that you need to make to understand the distribution of the ships in the battleship. So now imagine that we have three-dimensional battleship. So how many fires you need to make to understand how everything organized in this space? Can you infer the trend? So how number of fires depend on the number of coordinates that we have in this feature space? Anybody can tell me what he thinks on that? So for example, if we have n dimensions, then the number of fires would be something like, try to think on that. Yes, so that would be 10 in the power of n, which, as you understand, grows extremely quickly. So for example, imagine that we have feature space of like 10 sensors measurements. This is 10-dimensionally feature space. So you see how much this space is, even if we just, even if one sensor can report you just binary information. So it's basically 2 in the power of 10 gives 124 combinations of the sensor values. And what if we have image? For example, if we have a small tiny image of face, which is 80 by 60, this is almost 5,000 dimensions. 5,000 dimensions. Can you imagine how big this space is? So to fill this space with examples, in order to really understand what parts of this feature space belong to the class face or non-face, you need extremely big number of examples. Well, the good news is that some feature values depend on the other feature values. So for example, adjacent pixels, they usually have close values. So therefore, actual complexity of the space is smaller than the number of dimensions. So if we could compress our data into a smaller number of values that still represent our object and use these compressed values for pattern recognition, that would be a great help for us. So how the classical theory, the classical image computer vision industry dealt with that problem. So they started to invent various handcrafted algorithms for describing image from various points of view. So they can describe the presence of corners, they can describe the presence of edges, some kind of blobs in the image, regions of uniform lighting, and as many of you heard about the shift descriptor, which is intensively used in computer vision, that allows you to have certain points in the image which look stable in different orientations to describe the distribution of image information. And just to make you understand how big of handwork was done in that area, I wanted to quickly, on a fast forward, rewind you the typical presentation from the computer vision field, how they study various features, their algorithms, how they work, which are their drawbacks. So they compare various formulas, they try various things, then they see how good and bad are them in this situation, in that situation. And it's just a big, huge world of the various feature extractors. So for every next problem, you had to select certain features which better allow you to sustain with certain aspects of your objects or the transformations that your object has, and so on. So this is very inconvenient because you have to program this code for the feature extractors every time you face a new problem. So with that features, if we had these manually handcrafted features, then the object recognition problem is used by the fact that you analyze the features, build some kind of histograms of their characteristics, and then put into the classifiers. And what issues we have with that? Well, first of all these features, most of these features are empirical. That is, just smart man looks at the image and says, what if I do this or that? Well, at first, the smart people cost a lot. They are not always available, and really ones need talent to do this, where every person in the world can recognize objects without no problems. So there is some kind of issue here. It should be simpler. And this does not work in non-natural domains. For example, if you have infrared image or multispectral image, the intuition doesn't really work here. So you can't just decide on which features to take just by looking at the data. Or if the data is represents some kind of sensors management, radio wave sensors management, X-ray, where you don't have any idea what to look for even. And the second issue is that this handcrafted code is usually sequential and it's not always scalable. So for example, code that detects blobs in the image, the stable blobs in the image called MSER, maximally stable extreme regions. This code is based on trees. So the trees are really not very good parallelizable, as the operations of joining trees are difficult to make in parallel, because the results of the operation on trees depend heavily on the previous operations. So if you analyze image sequentially and build some kind of tree, then it's almost impossible to put that on GPU, for example. Again, another problem is that handcrafted features like SIFT, if you try use it for another domain, for infrared, say, for example, domain, you will not use the specifics of the infrared. So that kind of sensor has its drawbacks and advantages that you better use in your when you work on the features, which you can't. So, oops. So that's, for example, examples of sensor from a different domain. It's infrared, range data, and so on. So to stop working on these handcrafted features, we need to, as I said, make some kind of system approach to this problem. That is, if we take a top-level view on what we are doing, is that basically we have a big vector that describes initial data that we get from the object. And what we ideally would like to have is some kind of smaller size, compact representation of the data, something like zipped version or compressed version of our data that would be much less dimensional than the original one. So if we formally write what we have, so we describe so-called the concept of autoencoding. So the autoencoding system consists of encoder and decoder. So encoder basically compresses our data into some kind of hidden representation. And then the decoder should be able to take this hidden representation and reconstruct our original data. So if we're able to train the system on the data that we collect from our sensors to minimize the difference between input vector and reconstructed vector, taking into account that the data passes through some narrow bottleneck where the dimensions are lower, then we basically solve the feature extraction problem. We find some numbers that represent our data well, which is encouraged by the fact that we can reconstruct our original vector correctly. And this hidden representation of the original vectors can be already used for the subsequent pattern recognition task. Later, we can basically cut off this decoder part, just throw it away, and use only the encoder to make the classification problem, to recognize our patterns. When I say throw it away, it's just indeed, for example, you can have a composite object that consists of two objects. They work while training, and then you just call physically the destructor of the decoder, and you don't need it. So you have just the encoding object that you work with for pattern recognition. So how, yeah, sure.
Isn't there a bit of a problem there in that your initial vector will have some parameters which are just noise?
Yes, and this is very good because when we
It won't necessarily be reconstructed accurately because the noise is irrelevant.
well, since the output, the desired output must match the input vector, then the system would not be able to capture that noise. So, well, I will explain it maybe after the session. It's about, there are different approaches how to handle that. For example, we can add noise here and require that the unnoised vector gets out of here. So we artificially add noise to the input vector and then require that the clean one would be reconstructed. In this case, the system will learn how to use multiple sources of data for the same region to cancel noise, like by averaging, for example. So how to do this? Well, the simplest way of solving this outer reconstruction problem is a famous principal component analysis approach. Can you raise your hands if you know about this approach? Okay, about third. So I will take a little time to explain that. So suppose we have data in multidimensional space which has correlation. In this case, we can find a new system of coordinates where the most there is a direction where data changes the most, and there is other direction where we have smaller number of changes in data. And so by throwing out the dimensions where data doesn't change, we can basically reconstruct the data by just using information where the point lies on this major axis. So basically the procedure of encoding in this case would be to project all points on this major axis, and the reconstruction procedure would be to return from this system coordinate to the original one. And we will see how it works in a little more detail soon. Well, I just wanted to say that, for example, we can, one of the famous examples of application of PCA for pattern recognition is so-called eigenfaces problem, where we take multiple faces of people and create a new system of coordinates that represent the most changes of the pixels for faces specifically. And it happens that if original feature space, say for images 80 by 60, has about 5,000 pixels, then the study shows that about 100 dimensions, if we select them by the most changes in data, represent faces with very good accuracy. So that in this case, we can throw out all our other dimensions in this new system of coordinate and receive the compression rate of almost 50. So the early face recognition systems were based on this principle. Now we can see how this works in a small Excel exercise so that you better feel what it is. So for example, we have here a data set, two-dimensional data set that we want to compress with PCA. Well, PCA is a linear method. Basically, to receive new system coordinate, you need to make multiplications and additions with the original data. So the new system of coordinate can be found by a linear algebra. Well, in this situation, I will tell you that this can be also received by solving an optimization procedure, which is for some people who are not familiar with linear algebra would be easier. So on the right, we have the desired hidden representation. So we want in this column to have just one dimension which would represent data in such way that we could later reconstruct again 2 dimensions just from one. So we write the linear dependency of this hidden representation from the original data, and then our columns for reconstruction also have linear dependency on the hidden representation here. So far, the coefficients of these linear transforms are written in these cells, and they're just taken random, so the system does not do anything useful. We can see that in the untrained case, the vectors are reconstructed very poorly. For example, the first coordinate of second feature is minus 0.5, and here it's 1.99, so nothing close. So we use the Excel optimization procedure to minimize the errors of reconstruction written in the last columns by varying these parameters here. So we run this solver thing, and here the red points represent these reconstructed points. So basically we see that now this hidden layer, hidden vector has condensed our 2-dimensional space into 1-dimensional space. So every value here represents 2 values here. And then so these 2 reconstructed values, they are only computed by just using one value in this hidden representation. So you can see that the cell only references just one column. And we can see that the error of reconstruction after the training was minimized. So basically, the distance from this line is actually our representation of our error level. So this is how the linear method works. We can apply it to lower down the number of dimensions. So that's the first way. But you see that it's not very perfect. If data is curvy, then we have some problems. The second issue with the linear approach is that sometimes it may kill important class discriminant information. For example, let's consider this data set where 2 classes are separated in the direction of small variability of data. So in our case, all of this, if we make PC analysis, all these examples will be projected on this major axis and will get messed. So in this downscaled feature space, we will not be able to differ examples of one class from another. Well, for this particular situation, a nonlinear approach could help us. So if we would be able to construct a curvy system of coordinates where we would project all points on this curvy axis, then in this one dimension, we would be able to separate points with a much higher accuracy. So how do we do that? In order to do this, we will construct a small neural network of this architecture. So we will have just one neuron in the first layer, which takes our two inputs and perform the multiplication, addition, and computation of nonlinear activation function. So this will be one-dimensional hidden representation of our two-dimensional data. And then we will have one output layer of neural network that does nonlinear reconstruction from this value. And the last linear units are just used for that we scale outputs of the neurons to the range of values of our original data. So these ones are just auxiliary for basically scaling up to the original ranges of the values from the original data set. So let's see how this can be done. It can be done in a very close manner. So again, the same data set here, two-dimensional data set. Now, there are coefficients of the encoder units. So just 3 coefficients because it's multiple of one coordinate, multiple of the other coordinate, and bias, that is shift. And then to decode from this hidden representation, we need, again, 3 coefficients for one neuron and the scale, and 2 coefficients for one neuron and final shift and scale, and 2 coefficients of the other neuron and final shift and scale. And we just use the same solver, that is optimization procedure, to find the coefficients of this neural net. So basically, right now we will train a tiny neural network that must do the data compression here right now. So we run the solver. We say to optimize this cell, which represent the error of reconstruction, by varying the coefficients of the input layer and input hidden layer and output reconstructive layer. So we find solution, okay, and we see this nonlinear representation of our data. So basically, we found curvy system of coordinate onto which we can project our data and then reconstruct it with much, much higher precision, much, much higher accuracy than just a linear approach. We can compare that with the PCA. In PCA, we got sum of square differences of initial and reconstructed data on the level 0.22. And you can also visually see that we have big discrepancies for many points here. And here, the error level is 0.07. So it's almost 3 times less than in a linear approach. And you can also see that average distance from the original point to this curvy axis that we created is much smaller. Okay, let's move forward. So now you understand that neural networks are capable of compressing data and finding hidden representation of our data with great accuracy. They are capable of capturing nonlinear dependency in our data and form hidden representation of our data of much smaller dimensionality than the original data was. What is more interesting that we can now apply this technique recursively to our data. That is, after we had this encoder of the first iteration, we can take this hidden representation received from that original neural network and put it to the next autoencoder. So that has task to reconstruct already this hidden representation. Yeah, so on the first iteration, we tried to reconstruct original data through this hidden representation. And on this step, we try to go further. We ask system to reconstruct this hidden representation with another neural network autoencoder. And so then we can also cut off this decoder part here. And we don't need now intermediate computations. So we have coder 1, which feeds his output to the coder 2 and receive next level of condensed representation of our data. And we can do this recursively many times. So each autoencoder compresses our data more and more and finds more and more high-level information dependency in the data. We will talk about this a little later. We can also, as earlier I said that we can cut and throw away decoders. But we can also keep them, and just to verify that by decoding this hidden representation several times, we, in fact, are able to return to original data. So we can reconstruct our original images or signals from sensors with this stacking approach. Why do we need many layers? Well, because each layer, due to that non-linearities existing in neural elements, in neurons, are capable of grabbing more and more high-level information and data. So, for example, the first layer neural network just grabs edges and point features in the image, some kind of color distribution things. The next layer may be computing features out of the features of the first layer by combining them into pieces of objects, basically. And going further, we get high-level features that already represent some kind of logical relationship in our data. Finally, these high-level features have very little dependency on the position of the object, on its lighting, and so on. So they are very good for building pattern recognition problem.
Well, I'm really sorry. Can you go back to that previous slide and just explain what all those images are? I don't understand any of it.
Can you, maybe you can also sit closer, there are some places over here.
I can see it
Yeah.
I don't understand it.
Okay.
It's relevant. So there's a car. I just need to be talked through what that's telling me.
Okay, well, don't pay attention at this car at the moment. Pay attention at these color pictures. Yeah. Well, these color pictures represent weights of the neurons after the neural network was trained. As you see, the
so each of the small squares
yes, is one of the neurons in the neural network.
Right.
Basically, we visualize the weights of the neurons in the neural network. We see that each next layer has learned information of a higher logical dependency on the data. So the first layer learned local dependencies of the data. And then the next layers learn the combinations of that. And final layers learns the combinations of combinations. So they basically are capable of capturing parts of the object classes. Is it any better now?
Yes.
Okay. Okay. So now, after we made this feature extraction, after we made this feature extractor, we are capable of using classical pattern recognition theory, train our classifier on the labeled data set, and then use it to classify a new object. But look what happened. The principal point here is that we already have much less dimensions here. This is number one. And the number two, that we did not have to label anything for the feature extraction part. We can use unlabeled data to make this feature extraction unit. And then we can only label small number of examples, because here the dimensionality was greatly reduced. We have a breakthrough this curse of dimensionality already, and these dimensions are much smaller, and so this means that we can pay less for the people who will be labeling data sets for us. This is a very important point here. So we did most of the hard work by unsupervised system, which was just watching at images. We didn't have to tell it which class the image belongs to. And this is a very important point. So we were able to, as humans, we were able to self-train the system that it was just receiving the data, looking at the data, and understanding the internal relationships in the data without human intervention. Yes?
That's not exactly true, is it? Because, for example, you may not classify the images. You know that the images must belong to particular classes.
Okay.
So, for example, if you want to separate cats and dogs,
Yes.
you know you have to have images of cats and dogs.
Yes, but you don't have to label them. It's just.
Yeah, but someone has to say they're cats or that they belong to the.
No. On this particular part.
No, I understand that.
Yeah.
Someone has to say, here's an image of a person. We won't use that. Here's an image of a cat. We will use that. Here's an image of a dog.
Yes, but this is.
So somebody has labeled them.
Yes, but this is.
You don't tell your algorithm what the labels are.
Okay. I understand what you mean. The thing is that how this that example with cats and dogs really is simplified. How this works in reality is that usually such systems are trained to work for a big number of classes. So we just take natural images, which has cats, TV sets, cars, and things like that. And we submit all that into this autoencoding cascade. And there is a so-called convolutional principle where we have, we can make an analogy of a sliding window that examines parts of the images and learns to extract features for any type of the natural object present in the sequence. So we don't have to, it's easy to make lots of shots. The expensive operation is to take image, find objects manually, put it in a rectangle, and then classify. That is costly. But just push button and make natural images is not very expensive thing. Yes?
Wouldn't it work anyway in that, even if you presented pictures of human beings, chairs, you're really creating a system that only differentiates three classes, which is cat, dog, or neither?
You see, you don't have to actually. I would say that if we need to switch to, for example, infrared domain or multispectrum domain, then yes, we will have to select different classes of objects. But to differentiate between humans, cats, furniture, we can take natural image photos without really caring for if we take tables or we take chairs or we take cars. All these objects have certain elements that describe themselves. that these deep neural networks are capable to capture. So the set of images used to create this feature extraction can be much wider than actually the pattern recognition tasks that we solve here. So we say like this feature extractor learns features to describe natural objects. And it's not really important if we were to classify cats and dogs, and we found mouse or a human in that. Just some features here will be devoted for this class, but anyway, certain features will present to find fur, mustaches, tails, legs, and so on, and that all will be useful for classification. You are right in the sense that just 1 second, you are right in the sense that if we want to tailor system specifically for cats and dogs, then yes, we can do extra work so that we don't have to bother with other objects present in natural scenes. But usually the task is more general. It's like take a picture and ideally recognize everything that we see on this picture. Please.
So, if I understand correctly, so the deep neural networks are auto-classifying anything?
They prepare features to classify anything.
Yeah. But ultimately, if you want to know that was a cat or a dog, you have to label it.
Yes, yes. In the end, yes. So this is only for feature extraction. Later, you can label, but you can label much less examples of cats and dogs than if you would try to feed the pixels into the classifier. That's the main point. And so, for example, to build a system that takes pixels, you need thousands and thousands of examples. After you have features, then you maybe need just a few dozens of examples. So you drop down the number of manual labeling process by orders of magnitude. Okay, next one. So that's, for example, how real-life deep learning networks look like. They have multiple layers of often different architectures, so-called convolutional layers, fully connected layers, pooling layers, and so on that do this work in a really multidimensional manner. And the recent applications of these, recent tests of these architectures show the outperformance of the systems that were used handcrafted features. For example, one of the classical examples is so-called CIFAR 10 dataset, which is often used for benchmarking pattern recognition system. Has these examples of natural objects, and you see that they have completely different orientation, background, spices, and so on. And it's wonderful that deep learning architectures can solve this problem with more than 90% accuracy. I can show you a live example. I think I have it open. Well, that's one of the frameworks that I have listed in the end of my presentation for you to consider, called CAFE from Berkeley, where they already pre-trained deep neural networks for classifying natural images. And this link is available for you. You can try it yourself. For example, I just tried it on my images that I had on my laptop. For example, this one is a shot from my summer house where I had this equipment for warming things up in my house. And you see that this one was able to correctly identify objects on this natural image it says that it's measuring instrument. It has thought that this one looks as clock. Well, I don't think that we must punish it for that. It really has numbers and round and arrow here. But what is more interesting that it was even able to define barometer, which this system, well, actually that's not barometer, that's thermometer, but I think that's amazing anyway. Let's see what, I just selected a few other examples. For example, this man over here. It doesn't seem that they made faces detection a target in their system, so it never says that there is a face, but you can see that it was able to understand that there is clothing here, necktie, and consumer goods. I don't know what is that. Maybe that's glasses or something like that. One more example, interesting here. It's from an advertisement, which is a man driving Mercedes machine. So for some reason, it understood that it's wheeled vehicle, motor vehicle, and container. I guess this is for the head of this guy. The helmet was classified as container. Well, which is sort of true. That's container for the head. The last example I will show here is this image. Again, it did not detect a person, but it was correctly able to find clothing and consumer goods in the sort of that there are some clothes hanging on the background, which I guess rise that thing up during this classification. So this does work, and this was just recently released in the end of last year, and it evolves intensively. What's good about this Cafe library that it's open source. You can download that. You can try to feed your own data, and unless you write derived code, I guess you can use it for commercial applications as well. The little problem with Cafe is that it's Linux-based. There is some unofficial port on Windows, but basically it's for Linux. So this is a little. I guess this is a little inconvenient. Let's then. Well, we had some relaxation. Now I want to feed some more into your heads, if you don't mind. I wanted to represent you another interesting approach for classification objects with autoencoders. As we have now a small dimensional representation of our data, we can make a different approach. We can try to feed data of a certain class into a separate autoencoder. Yes, that would require sorting items, as you mentioned earlier. But in some cases, this is inexpensive. For example, if these are images from a CCTV camera, and for example, car gets to a certain place, then you may have multiple frames of that car. And then if human gets there, you may have just a range of first and last frame marked, and then you have a bunch of examples of a human and so on. So in some cases, this is not expensive. You don't have to mark individual, like this is a hand of a person, this is a wheel of a car, so that's not required. Just images of these objects. So for every class, we can train an autoencoder that would represent its condensed representation in feature space, so-called subspace. And what we do then is that we classify new object by measuring the reconstruction error. So we submit data from the object to these several autoencoders and see which of them reconstructs it in a better way. For example, consider this point over here. The distance to this curvy axis would be smaller than to this one or to this one. And the point which belongs to this area of feature space would be then classified as this upper class. I can now show you a live example how this works, how this approach works. So that's a really live demo. Live demos never work in actual situations, so I'm a little bit afraid, but that's I'm here for, and I wanted to show it to you. We talked about that classical image recognition approaches required selecting features. So for example, I have here different examples of well, not quite natural, semi-natural objects. And you can see that some of these objects, for example, have no corners. This object has no corners. You agree, yeah? If we consider the internal part of this textured matter, you understand that it doesn't have corners and it doesn't have any kind of form. So these flags here, for example, these two or even these three cannot be recognized by using color features because they all have these white, red, and blue colors on them. So it's not possible to recognize them with by just using the color histograms. So let's start with these flags first. There's an area where I can demonstrate and collect by pressing button. I collect examples of the British flag. So the number on the right, it's 70 and running, represent the captured examples of the British flag with various orientation, scales, and shifts. So we're done with capturing examples of this first class. Now let's start with the other example here. Again, we collect examples and we collect them in different orientations, shifts. We move forward and backward so that the system has enough examples of this object. And the third one here, we get this one, again in different orientations and scales. We need to collect about 100 frames, a little bit, maybe a little more. Okay, so we're done with the third one. Now we can take just a few frames of background so we can differ these ones from background. I'm done. And now I start training. That's online training of neural networks where we can visualize states of the neurons of this autoencoder. And first of all, we train this first-class autoencoder that learned different variations of this first object, which was, I recall, British flag. We can see that this is a running output of the computations. Now we get to the second class, which is American flag. We see how neurons learn the specifics of that class of objects. And the running MSE here, it's decreasing, shows how well autoencoder can encode input image with these 40 outputs of hidden layer. So basically, the image, which is about 120 by 80, so this is almost 8,000 dimensions, are compressed into just 40 numbers in the hidden layer. So we're almost done with this third flag here. And you can see that this software runs quite quickly because it uses Intel math kernel library that accelerates matrix vector multiplication. So even on this laptop without GPU, computations can be accelerated using various performance libraries that accelerate matrix multiplication. So these professional deep learning networks usually use GPU heavily to accelerate computations because they have multiple vector matrix vector operations which are very easily accelerated on GPUs and multi-core processors. So now we can start testing our system. So for example, let's see. Here we see the way how neural networks reconstructed images. So this is unknown background. This is autoencoder for class number 1, for class number 2, for class number 3. And this is input image. So you see when I show the system British flag, the best reconstruction is done by the first autoencoder. It represents British flag most closely to the input image. And we see that class 1 message in the middle of this frame with the blue letters that says that it is correctly recognized as class 1 unless I do some extreme modifications of this object. So it can recognize it rotated in various scales. So when I take it away, it says class unknown, which is our background autoencoder. Now, let's see, that's the second one. And we see that it's better reconstructed with the second autoencoder. And it says class 2, again in different scales and rotations. So I move this away. And the third one here, look at how well it is reconstructed by the third autoencoder. So this image, this image below looks most closely to the input over there. So that's how I just wanted, why I show this example is that you better understand how autoencoder works. It can be used for pattern recognition, but that's not a major point here. I just wanted you to see how autoencoders can be trained and how they work. Now let's try to see another case where, for example, we wouldn't have corners. I need to shut down this program and run again. So let's try to, for example, differentiate between these two objects here. It will take us less time in this case. So let's try to collect images of this round object here. So you see, I just used the same software. I did not plan or think about what kind of features to use for pattern recognition. So I just showed examples of these objects in various scales and orientations and lighting. So that was object number 1. So this object does not have any kind of form. So it doesn't have any counter that the system could use to classify it from another one. So it represents example as if we would turn into a different domain. For example, if we turn into the frequency domain, we will not have much information on the edges, just the frequencies. Okay, and a few background images, 1, 2, 3, 4, 5. Okay, done. Now we start training. You see the autoencoder for the first class tries to understand the variations of the round object over here. So it creates features that can capture round edges of the object of this first class. It soon be done. Maybe I took 2 more images, a little longer. So that's the next the next autoencoder, as you see, captured here periodic structure of the object, and also used some neurons to capture color of this meta. Some light neurons here, for example, use this higher background state to represent variation in differences in lighting conditions. When I turn the angle of the object, its lighting changes. And this is just a third one to capture the background. So we now try to turn the classifier on. Oops, sorry. So you see that's an input image on top. Then how it is autoencoded by the second autoencoder, by the third autoencoder, and by the background autoencoder. So now we show it this object, and we see that it's best reconstructed with the first autoencoder, and it shows class 1 here. Now we show this object without form, and we see class 2 under different scales and variations. We can even get closer than we were during the training, and it still says that it's class 2 because it captured the periodic structure. So angle doesn't matter, and even some background happening on the edges of the image do not much influence. So this is kind of quite stable recognition here we observe. So now you can feel how these autoencoders work. So this was just a very simple example of a single layer autoencoder. And you can see that even one layer of the autoencoder has great power of extracting class discriminant information, and much more power can be received from these stacking autoencoders. Now let's make a resume. And we saw 2 different approaches how to classify with autoencoders. The major differences are here is that when you make a stacking autoencoder, you feed examples of all classes into that for the sake that it will find the features that are suitable for any class. And after that, you use pattern recognition in the end of this, which uses extracted features to recognize from one class to another. The other approach that we saw now is that you train separate autoencoders for separate classes. For each class, you train your own autoencoder. And you decide on the class membership based on the error of the reconstruction, how well this autoencoder reconstructs your object. If you start reading about, don't be afraid of that, we will not go into the details. If you start reading about deep learning architectures, you will definitely read about the concept of regularization. And I just must say a few words about that. What is regularization? It's another specific constraint that we want to put on the hidden layer so that our hidden representation gets some kind of useful properties for recognition. Invariance, independency on the transforms of the objects, and so on. Basically, these regularizations are like spices of a cooker who wants to give the dish a certain taste. For example, this regularization formula is another constraint that can be put on the hidden layer outputs that minimizes the dependency of the hidden layer outputs from small variations of input signal. And this allows to make this hidden representation independent of small changes in scale, in size, and so on. And so right now, the tendency in deep learning is basically to study various forms of regularization, how to further improve and shape this hidden representation so that it works better. For example, in our company, we study specific forms of regularization that tries to separate meaning of the hidden neurons so that a certain part of the neurons would be responsible for information about class, and certain neurons in the hidden representation would be responsible for changes, for transforms of these objects. So if lighting changes, we want these particular neurons to change, and these remain the same. And if we have two objects with the same lighting conditions, but of different class, we want these neurons to output the same data, output the same numbers, and these to change as the class has changed. So that's where the current studies go in this direction, and that's what is being studied right now in the society, where this go. One interesting point that I need to also mention here is that when we constructed the whole pipeline, that is feature extractor and then recognition system, let me find this in our slides, this one. So from the beginning till the end. If classifier is a neural network, then all this is just a big, huge neural network. There are 2 points that I need to discuss here. The first point is that we can further improve accuracy of recognition by so-called fine-tuning the feature extractor. Since all this is already connected into the neural network, in the common neural network, we can try to apply gradient descent learning, that is error minimization procedure, just as we applied it when trained our classifier here, to optimize further weights which present in the feature extraction layers. It shows that this fine-tuning step can give us another 5–6% of accuracy, which is significant for many tasks. And the second point that I wanted to discuss here is that you can ask, so why don't we just take a huge neural network and try to put it into the learning algorithm and train it without all these autoencoding approaches and so on? So I can tell you that this is actually this was approach which the Scientific Neural Network Society tried to do after 90s. So before 90s, computers were too slow, so they weren't just able to operate with heavy neural networks. And after 90s, scientists started to try to learn huge neural networks in supervised manner. And what they found is that it doesn't really work well. So when you try to train a huge neural network, the error information backpropagates from the end to the first layers, and by the time this training information reaches from the end to these first layers, it vanishes because of all these cross-connected neurons, and basically the initial layers learn very, very poorly. That's another case of the curse of dimensionality. in this case, the problem in the big dimensions of the weight space. So if we think about the weights, the coefficients that neural network has, it can also be portrayed as a highly dimensional space where the certain point represent the state of the whole neural network. And when we try to train the whole neural network at once, we again face the same problem of high dimensionality that is difficult to find a certain place in this high dimensional space. So this staking out encoders deep learning approach actually solved that problem. And it gave us an instrument that we can sequentially train the system layer by layer and form this multi-layer, highly nonlinear classifier without stacking into this problem of training very deep neural networks at once. And after this approach was proven to work, immediately the popularity of neural networks rose by the order of magnitude. Because in the 90s, there was like a bump. Everybody was trying neural networks for every problem. And there were lots of publications that neural networks now can solve everything. But the accuracy rose to like 80%, which was enough to make a good publication. But it was not enough to make a practical application. And so after 2000, these handcrafted algorithms started to gain popularity. And they evolved very intensively, these SIFT descriptors and so on. All this field has evolved intensively until about 2006, where the concept of gradually trained neural networks with staking out encoding concept was introduced first. And after that, again, scientific society switched to deep learning networks because it's a handcrafted code killer, and it can be trained in an unsupervised manner, and overall it's the right way to go in the pattern and image recognition. So this is the most intensively studied field right now, and a big help for this study is the recent appearance of hardware accelerators and cloud computing, as big neural networks require lots of computations which can be accelerated on GPUs and clouds. The handcrafted features, I must say, they work faster than deep learning neural networks. So I would say that the top GPU-powered neural networks work at about the same speed as the handcrafted feature descriptors just on CPU. So there's still some gap in performance, I mean, in terms of speed of computing between handcrafted systems and these autoencoding and deep learning systems. But hardware cost gets lower and lower. The GPUs obtain more and more streaming processors every year. So eventually, that's a way to go. People will soon, I guess, refuse to use these handcrafted approaches in pattern recognition and more use artificial neural networks that study that can be trained in unsupervised manner. So I guess I need to show you a few frameworks that you can find in the internet. It's in the last slide. Very good tutorial on the internal math, how things are constructed. And those of you who maybe wanted me to tell you more accurate mathematical formulations. Another interesting approach where the first layer of neural networks is trained with the clustering algorithms. So Adam Codes has this MATLAB code where features are extracted with clustering approach. Then three deep learning frameworks which are often compared to each other in the internet. They're all free. You can download and use them. So I said that Cafe is C++ Linux based. Python says by itself. And Torch is oriented at using its own language for matrix vector operations. There is a solution for our project users in deep learning. And recently, NVIDIA announced its digits package, which is very, very user-friendly system. Basically, this system starts your own local web server with the forms where you can upload and manage your data set. Just with clicking HTML pages, train the system and get results visualized. So everything is for you. You can use that freely. Well, I guess we have done the lesson. What are the questions? Do you have any questions right now? Okay, please.
I'm just wondering, are there any indications that the stack auto-encoding system actually is the way we do it? I mean, does it matter? Are there indications that algorithms work in that sort of way?
Yes, I understand. It's not really, the brain is constructed way more complex than deep neural networks. But neural networks, the deep neural networks get, again, more and more complex. For example, recently, a new concept in deep learning was network in network. So just within one convolutional neuron, they found that another embedded neural network can be used to improve the behavior of a single convolutional neural network unit. And that maps actually, one of the bioscientists were laughing at neural network scientists, saying that the brain is not a plain neural network, it's a network in networks. So now deep neural networks have also networks in networks concept, and that will evolve and evolve. So hierarchical representation of information processing in deep neural network will slowly match the processing mechanisms in our brain. So I think that maybe in 20, 30 years from now, the scenes that we saw in such movies as I, Robot, with these walking creatures who can talk and freely operate objects around us are quite possible. They will not have spirit, or not sure if they will be able to make conclusions and make some kind of deep thinking, but operating objects, talking to people in real time, that's quite possible soon. Okay, any other? Please?
Can you give some examples of how you've used deep learning in commercial applications?
Yes, for example, we used deep learning for a system that detects logo in TV translations. That is where the system collects statistics on how much different products were presented in TV streaming time. Also, we used autoencoders to detect famous politician faces in TV stream. And I guess that, well, these are just commercial applications that my company did, but I think that since these guys here offer consulting just on their websites, that they say that our programmers can do consulting work for you, it means that they probably have commercial clients as well. These frameworks are known to be used in commercial applications, just I don't have right now information about specific projects that they did.
the Microsoft translation strategy?
Yes, yeah, that's a very good example. Microsoft has announced their recent speech recognition engine, fully based on deep learning. So after this, they claim that they outperform Google's engine that was used for web searches and so on. But Google now intensively uses deep learning as well. So basically all companies, Google, Facebook, Facebook uses deep learning for faces statistics collection. So yeah, this is quite intensively used right now. So this is not just theoretical thing. Although I can say that these companies usually use it because they have a big amount of training data stored in their web archives that they can put through the deep learning architectures. And they have clouds where they can accelerate computation of these deep layered neural networks fast. So maybe for a small organization that needs I don't know, cell phone application that works very fast, doing a deep learning approach can be complicated. But nevertheless, just recently I saw a framework on C that accelerate deep belief networks for iPhone. So I just read about that yesterday. So they report that they can do object recognition within 300 milliseconds. So 1/3 of a second, which is not that bad actually. And that worked for iPhone. So yes, these solutions will come to our real life very soon. Okay. Thank you very much. It was a pleasure to see your attention.